Welcome to the course on fundamentals of MIMO wireless communications. Till now we have seen the expression of capacity for two important cases. In one case it is no channel state information available at the transmitter, where we said the best strategy is to put equal power across all the transmitting antennas. The second case would be when you have the channel state information at the transmitter and then the channel modes are all accessible. In that case the gross result that we got is it is better to do power allocation across the different antennas, and the best strategy to do power allocation is to put more power on the channel which has better channel strength. So, and that was a result of the water pouring algorithm which we had shown in the previous lecture. So, we carry on with those concepts, and what we are going to discuss initially is about mechanisms or techniques by which you could achieve those results, and then we will move on to see the effect of correlation on MIMO channel capacity, and also we will move further to look at the random MIMO channel and what is the outcome on capacity, or how do we represent capacity under those conditions will also be looked at. So, when we take the MIMO transceiver system, again I draw the transmitter with multiple antennas at the transmitter, and at the receiver we have multiple antennas. So, the first scheme we said is when there is one directional flow of information, no feedback information. So, in that case there would be signal S1 up to signal SMT that gets transmitted, and the signal that is received Y vector would be H, that is the matrix channel which lies between the transmitter and the receiver, Y1 up to YMR times S plus noise vector. This is the expression that is received. So, if we are to transmit these signals, that means we have to put equal power. That is what the expression gave us. The result that we have got is basically putting equal power, but it never told us how you can send symbols across these lines or these parallel channels so as to achieve the result which we have shown. So, the mechanism that we are doing over here is we will be sending S1 to SMT, that means different symbols. So, we are directly sending the different symbols S1, S2 up to SMT, let us say, and we have this channel matrix plus noise across this. So, if H is orthogonal, that means if the channel coefficients are orthogonal, then one of the simplest strategies to receive this would be to multiply H Hermitian with Y. If we multiply H Hermitian with Y, we are going to get H Hermitian H times S plus H Hermitian noise, and that would result in H Hermitian H would be identity matrix. So, we can get an identity matrix times S. In this case of course, with our notation we are going to have ES by MT root over ES upon MT right. So, H Hermitian H is so we have an identity matrix over here, and we could also have zeta upon M, so that the trace ends up as M. So, we could also have the total channel strength constraint, that will be a scalar modification of this. So, when we expand this will be H tilde N tilde. What we have over here is a diagonal matrix. So, each one that we receive, this one would write Y1 tilde is equal to root over ES over MT times SI, right, because it is a diagonal matrix, times N tilde I. So, what we can clearly see from this expression is that any symbol that is received in the corresponding branch of the receiver is not having influence of other symbols, whereas in a typical MIMO communication, whatever is being transmitted from all the antennas get added up together in any one of the antennas. So, if the channel is orthogonal, you can get that. If the channel is not orthogonal, the other simple way of getting back the received signal would be to multiply H inverse if H inverse exists. So, we can assume it a full rank M cross M square matrix. So, that is for one particular case. H inverse Y would give us S plus H inverse n. So this is the zero forcing mechanism. So even in this S is a vector. So basically we have yi cap is equal to, this is basically the vector which is y cap, you can say, is Si plus n tilde I, because this will again be a vector. Of course, this n tilde we can put n double tilde, which is different from in this case. Here again we have avoided interference, so there is no interference of the symbols. If it is non-square, then one could use H Hermitian H whole inverse times H Hermitian multiplied by y. In this case, if we are going to do this kind of an equalization to make it square, the end result again would be S plus, which is the pseudo inverse H inverse H Hermitian H inverse times H Hermitian times n. So this is what is going to be your received vector. So here again yi could be Si plus n, you could write triple tilde I. So here again in this format we are not getting any interference from any other symbols. So in this way one could reconstruct this. One could also use an MMSE kind of an approach, where one would use I plus H Hermitian H n naught upon mt inverse times H Hermitian times y. So this is the MMSE approach. This way we would also get it, but there would be some minor amount of interference because of this channel condition. So what we have effectively is through this mechanism, which is also known as vertical Bell Labs layered space-time coding, also known as VBLAST. That means in short is a vertical Bell Labs layered space-time coding is the name for this, where you could send the symbols directly across the antennas, and at the receiver you could do different kinds of processing and recover the symbols without interference. Thereby you are achieving as if parallel transmission. And we would remember that this SNR is dominated or is indicated by lambda I, where lambda I is the eigenvalue of the ith channel mode. So if it is a square matrix, you have m parallel links or you have r parallel links depending upon the rank of the matrix. So this is one mechanism where you can achieve the transmission and parallel data transmission when there is no channel state information at the transmitter. We move on further after this to look at the second scheme, where channel state information could be made available at the transmitter. Tx and Rx. So basically here there is a feedback, and if we would remember, the result of capacity in this case told us that we have the feedback about the channel state information. So we can get the eigenvalues. Once we get the eigenvalues of H Hermitian H, we are getting indication of the channel strength of the parallel modes that we can send. So based on that, again we will be distributing the amount of power which is proportional to the eigenvalue of that particular mode of the channel. So here again we look at that we have S as the vector of signals to be sent. There is this channel H which gets multiplied with S, plus there is noise, and this is what is received at the receiver across the antennas. Here again, as we can clearly see, that these signals get mixed up and we have a mixture of signals at every antenna. Now what we have said is, when you have feedback, what we could do is we could multiply a V at the transmitter side. That means there is some processing with V matrix and there is some processing at the receiver with U Hermitian. This is what we had proposed when we had discussed that. So basically at the receiver we are going to get U Hermitian. U and V are unitary matrices. So then if you would expand H, H can be stated equal to D V Hermitian and U, and because of this U we have U Hermitian, because of this V we have V plus U Hermitian N, and this we could write it as Y cap. U Hermitian U is identity matrix, V Hermitian V is identity matrix. So we have D times S plus N cap, we can say Y vector cap. D is a diagonal matrix consisting of the singular values. So therefore we could write yi is equal to, of course, there is root over Es by m. I tend to miss this term. So, root over Es upon m sigma I S I plus n cap. So, this again we see through this mode we are not having any interference from any other term. So, in this case also we are able to establish parallel links between the transmitter and receiver, and hence in both these mechanisms that we have just now discussed, these provide us, you can clearly see the gain of spatial multiplexing. This is an important terminology in the domain of MIMO. So, clearly what we are achieving here is in both these cases where there is no feedback and when there is feedback, we are transmitting S1 to SMT in parallel. So, there is multiplexing, and this multiplexing is in the space domain. So, this is why it is spatial multiplexing, and here this particular scheme there is channel state information at the transmitter. Because of feedback we are doing some pre-processing or pre-coding, it is also known as pre-coding. So, this particular method is known as SVD based pre-coding. So, if we follow this SVD based pre-coding mechanism, in this mechanism we can achieve the capacity when we have feedback information at the transmitter. And of course, as has been said, we have to distribute the power such that gamma I, that means the power in this channel, is such that there is a k minus 1 over Es by mt n naught times lambda I. So, this is the kind of mt n naught is Es upon mt n naught. So, this is 1 upon SNR. So, this is basically the amount of power which again leads to higher lambda values, higher values of SNR. So, if we add this kind of power distribution along with this, then that would naturally lead us to parallel connection, parallel sending of signals, so that we achieve capacity of channel state information at the transmitter. So, summarily, when we do either of these two streams, we are sending parallel information. We are sending parallel information from the transmitter to the receiver. The number of such parallel links is clearly as many number of independent links available, and this is indicated by the rank of H. The rank of H would indicate as many number of independent links. There are many details to it. Sometimes it's not very easy to identify what is the rank of a matrix, and one would deal with the eigenvalues of H Hermitian. So, one would be interested to know what is the ratio of lambda 1, which is basically lambda max, to lambda min. So, this would give us a condition number which tells us what is the distribution of eigenvalues, and we have seen this capacity is maximized when all the eigenvalues are equal. So, sum zeta upon m, let us say. So, this is when it is maximized. So, we would like to see if this distribution is very large, then capacity is not maximum. So, we would like to choose the number of modes. That means, it may happen that I have 16 cross 16 system or an 8 cross 8 system, but if instead of taking an 8 cross 8, if I would choose a subset 6 cross 6, it could give me a better capacity, a better sum total capacity. So, that one has to try and see out of these combinations which is giving a better capacity, and one chooses, and this is one way of quickly circumventing the problem instead of looking around for all possible combinations. So, we have seen at least two ways of which MIMO channels could be exploited. First, we have seen what is the expression of capacity, and then we have looked at how the signals should be sent. The first mode is where you send the signals as it is. In the second mode, you would be doing some pre-coding. The pre-coding is based on SVD of the channel or the singular value decomposition of the channel, and you have to use the V matrix at the transmitter and the U matrix at the receiver, so that you get R parallel independent data pipes. And since you are getting parallel data pipes with the help of multiple antennas, these mechanisms are known as spatial multiplexing. What we had seen before, before looking at capacity, we had talked about diversity. So that was spatial diversity. So we have seen two very important things. One, through spatial diversity we are able to improve the error probability, and through spatial multiplexing we are able to improve the capacity. So with this we move forward and take a look at some more things on capacity. So the first thing we are going to look at is the influence of spatial correlation. Right. So we have seen that H, which is the channel, could be written in terms of the correlation matrix at the receiver raised to the power of half times HW, which is a spatially wide channel, times RT raised to the power of half. This is a spatially wide channel. So this captures the correlation at the receiver, this captures correlation at the transmitter. So of course we have RR, the elements ij set equals to 1 for I equals to 1. So basically we are saying that it is normalized, all these RR coefficients are normalized, and so are RT coefficients. RT coefficients are also normalized, and this would result in expected value of Hij mod squared to be equal to 1. So all we are saying is that the channel coefficients are normalized to unit power, and the expression of capacity that we have arrived at earlier is log determinant of I mr plus Es by n naught mt. We had H Hermitian. So instead of H and H Hermitian we had H Hermitian. So we could write RR half HW RT half for H. So when we have H Hermitian we would have RT half HW RR half, right. We have expanded this. So this RT half we could write it as RT, right. This is what we could do, and we will make the assumption that MR equals to MT equals to M, that is we will make the full rank approximation. So when we write it in this form, since it is the determinant, we could say that at high SNR this effect of 1 from this could be neglected. So we could say that it is dominated by this, because we are saying that Es by n naught is much greater than 1, because the determinant would be having the eigenvalues, and in the eigenvalues we are going to have the of one matrix and that of the other matrix. So basically this will lead to 1. So when the right hand side is much more than 1, we could say that 1 can be neglected, and this capacity expression we could approximate it to log 2 determinant of Es by m. We had said mt equals to mr equals to m. So Es by m n naught times HW Hermitian. See, now we do not have this, so we are having log determinant of these things. So log determinant of AB is equal to determinant of A times determinant of B, right, or determinant of AB is equal to determinant of A times determinant of B. So what we have is determinant of these terms. So determinant of these terms we have HW. So we have basically HW as one of the terms, plus log base 2 determinant of RR. This is clearly what we have, and then again we have RR half. So basically plus log base 2 determinant of RT, right. So if you put them together, log determinant of this times this times this, so basically we have this term, and that is the result of this expression when the right hand side or towards the plus of this is much greater than 1. Okay. So if what we see from this is the effect of correlation at the transmitter and at the receiver are basically similar. So if we study one of them, we can satisfy. So we can do either at the transmitter side or at the receiver side. So we will put the constraint that sum of lambda I R is equal to 1. So this is one particular constraint that we will maintain, 1 to m. So if this is equal to m. this is equal to m. So total power constraint is that we have to maintain. So now we will use one inequality, that means arithmetic AM GM inequality, known as AM GM, arithmetic mean geometric mean inequality, to our aid. So when we use arithmetic mean and geometric mean inequality, what we get is that if there is x1 to xn, a set of random numbers, a set of numbers, if we say. So if we take the average, we will find it to be greater than or equal to the root of x1, x2 up to xn. And what we have is in our case is sum of I equals to 1 to m, lambda I of r is set equals to m. So this is what we have, and according to the inequality that we want is 1 upon m sum of lambda I r, right. This is of course equal to 1. This should be going by this is greater than or equal to nth root of pi of lambda I of r r, right. That is the receive matrix. This is what we have set. Okay. So now if you look at this, this is equal to 1 according to this. This gives us 1 upon m, this equal to 1. So what we see is that square nth root of pi I lambda I r r is less than or equal to 1, or in other words, product of the lambda i's of this covariance matrix is less than or equal to 1, right. I equals to 1 to m. So if we apply this back here, so determinant of matrix, determinant of r r is equal to pi I equals to 1 to m lambda I r r, that is the product of the eigenvalues, and this is less than or equal to 1. So that means inside the log the argument is less than or equal to 1. So this whole term is negative. So what we have is a negative term and a negative term. Otherwise the best value that you can have is when they are equal. So that's the most best value that you can have. So basically you can have 1 as the best value. In that case this will be 0. So these being equal, all these eigenvalues being equal means that this is an identity matrix, and that being identity matrix means it's an orthogonal channel. Orthogonal channel means that R is not correlated. So when R is not correlated, this determinant will turn out to be 0. This will also turn out to be 0. This log of 1 would turn out to be a 0. So there won't be any effect. If there is any non-zero effect, that will only be negative effect. So that means the effect of capacity when we are studying at high SNR especially, that becomes very, very clear, is whenever there is correlation to be added in the terms, then the capacity decreases. We had also seen similarly, just to remind you, when we studied the effect of correlation on error probability, what we had seen, whenever there is correlation, the error probability increases. So what we see in both the cases, when there is correlation, in case of diversity gain, the error probability increases relative to the non-correlated case, but still it is better than a seesaw link. In case of MIMO, what we are seeing again is correlation reduces capacity gain, but overall still it will be better than a seesaw link. Okay. So these are some of the important results that we can gain over here, and we take a look at the result of correlation. So if we see this particular picture, what we would see is, so when we look at this particular picture, this is the case where correlation is set as 0.95, and this solid line is due to no correlation case, and if there is a 95% correlation between the antenna branches, this dashed line is what is there, and this is from the book Introduction to Space-Time Wireless Communications by Professor Palraj, Rohit Namar and Dhananjay Gore from Cambridge University. So I have taken this picture from that particular book. One could generate these results also. So there is a loss which is indicated by this particular line. So there is a capacity, so we will discuss ergodic capacity, about 3.3 bits per second per hertz, which is significant at high SNR regime. So what we can conclude from this is that when there is correlation, there is a loss in capacity, and this is well understood in terms of expressions when we look at high SNR regime. For low SNR regime also there is a loss but again we have taken high SNR. All these approximations that we are making is only to ensure that we get an insight into it, and from which we can clearly see, as we have seen over here, that these expressions lead us to certain clear cut understanding from directly by looking at it, and also which is supported by results. So now we take a look at the outage capacity. So we have seen this particular figure before, because C is random, as we have said. The capacity would be described more by its distribution, and at some point which is 10 percentile or p percentile, we would say this the corresponding value of capacity is the outage capacity, C out. So that means in this case we have taken the 10% outage capacity. So what we are seeing is that above this is 90%. So basically this side is 90%. That means 90% of the time the capacity is in this range. So this is a very important value, and it determines the lowest point in performance. Of course, ergodic capacity is what we have already described and seen how it is influenced under low SNR and high SNR region. So we will take a look at the outage capacity performance. So this is the 10% outage capacity performance for different MIMO antenna configurations. This side is the transmit antenna configuration, this side is the receive antenna configuration. So as we increase the number of antennas, so basically M is equal to 1, M is equal to 2 in this case, and M is equal to 4 in this case. So this is M. So we have M, right. So that means this diamond, this particular curve is M is equal to 4, and this particular star is M is equal to 2, and this particular line M is equal to 1. Right. So what we are seeing is that as we increase M, as M increases, what we can observe is as M increases, what happens to 10% outage capacity? That also increases. So basically the 10% outage capacity increases clearly. This is for M equals to 1, this is for M equals to 2, this is for M equals to 4. So clearly seeing that outage capacity is increasing. So if we are here, this is 2, this is more than 4. So this is one important thing. As you increase SNR, the outage capacity also increases. So this is one important observation. And if we look at the ergodic capacity, what we have is the same over here, is as we increase M. So here also is the same. This is for M equals to 4, this is for M equals to 2. So we are almost the same. Yeah, this is for M is equal to 2. Yeah, I think this is M is equal to 2 in this particular figure. This is M is, sorry, in this particular figure we have this one as M is equal to 2, and this one for M is equal to 1. Okay. So what we are seeing here also is capacity is increasing linearly, and as we increase M. So in both the cases it increases with M. Now the important thing that we are going to look at is here. So outage capacity increases with M clearly. So now suppose we have an HW channel. So for an HW channel, we have seen 1 by M HW Hermitian tends to I of M as M tends to infinity. So what does it mean? That a capacity expression, inside the capacity expression you have ES by M N naught and HW Hermitian, right, plus of course I MR. This is the expression of capacity for a given channel. What we had seen is that this tends to I. So if this tends to I, what is the meaning? The meaning is that the capacity expression is becoming independent of channel coefficients. So that means every time I measure the value of capacity for a very large HW channel and I keep changing the channel coefficients, the capacity value is not going to be different from each other. So under such situation, what I will see is under such a situation, what's going to happen is if we see this capacity axis, most of the time my capacity will be very close to one value, because what we are seeing is C is equal to log base 2 determinant of I plus Es upon m times n naught times HW Hermitian. So 1 upon m HW Hermitian, if that is equal to I, for m being very large, that is what we have seen, what do we get? Capacity is log 2 determinant I plus Es upon n naught, right. So that is capacity of a seesaw channel. So this is in the limiting case. So if it is not a limiting case, it will be very close to this value. So that means it will be very close to one particular value. So this distribution, which is so spread out, will almost be like this. So that means under such conditions, the outage capacity is almost equal to the median capacity, or in other words, what we can say is that under this case the capacity stabilizes. So all we are saying is that if we are able to provide a very large number of antennas, and if the link that we are providing is so what we have said is if we have very large number of antenna elements at the transmitter and the receiver side, and the links are spatially wide, that means they are orthogonal, what we can achieve is almost a stable link which does not vary, the capacity does not vary. So we are almost able to provide the capacity of additive wide Gaussian noise channel. So that is very important, and in fact it is m times the capacity of a additive wide Gaussian noise channel. So that means it stabilizes, the link is not fluctuating anymore. Similar situations would happen when there is line of sight, you are getting a very high signal strength, the channel does not the channel is very stable, there is not much variability in it, but of course there are different implications on the channel capacity. We have just seen the situation when there is low SNR. What we need to see now is the situation when we have very high SNR. So we take at the high SNR condition, we have seen it once, we will see it again in a more exact manner, and we will see certain interesting outcomes. So the ergodic capacity is basically expectation of log base 2 determinant of I MR plus Es by m n naught times H Hermitian. This is what we are quite used to now, this particular expression. So again, determinant being pi of I equals 1 to rank of H times rank of H of 1 plus root over Es by m n naught times lambda I, where lambda I is the eigenvalue of H Hermitian. Log 2 determinant is replaced by this and the expectation sign. So when SNR is high, when Es by n naught is very high, this could be approximated as Es by m n naught times lambda I log 2 determinant, right. So this you could also say is we could write it as expectation of so basically this term is constant. So if that term is constant, we will have RH, because this raised to the power of RH times log base 2 Es by mt n naught, this is the constant term, plus expectation of sum over I equals to 1 to rank of H times log base 2 lambda I. This is constant, so not of much importance. this is what we should look at. So what we are looking at is the ergodic. So when SNR is high, the capacity is determined by the spread of eigenvalues. So it is determined by two things: the rank of the channel and the spread of eigenvalues. Again, clearly this thing will be maximized when all the lambda i's are equal and when there is the full rank. So if rank is less, then capacity is less. So we would like to have full rank as well as a lesser spread of eigenvalues. So lesser spread of eigenvalues has multiple meanings. One of the meaning is if lambdas are almost the same, they are equal to, then we are having an orthogonal channel, which we have seen before. And all eigenvalues being same has another influence. So if you have all same eigenvalues, you can easily guess what would be the result when channel state information is available at the transmitter. So we have discussed that under such situation, when there is channel state information is available at the transmitter, we would like to follow the water pouring algorithm. The water pouring algorithm says allocate power to that particular eigenmode proportional to the eigenvalue of HH Hermitian. So if all eigenvalues are same, the power to be allocated in all the modes are again going to be the same, and that means that RSS would lead to identity. So again we are getting the situation when under high SNR conditions, we see that the power allocation would be equal amongst all the antenna branches, and that is the same whether you have channel state information at the transmitter or you don't have channel state information at the transmitter. So again what we say is that when SNR is very high, extremely high, under that condition the gap between no CSI at the transmitter and with CSI at the transmitter again reduces. So in summary, we have 2 points, that rank of the channel determines the capacity and spread of eigenvalues. If eigenvalues are very similar, you have very similar powers in all of the channels. Under that condition, the capacity of CSI at transmitter and no CSI at the transmitter would again be the same. So I would briefly give you an explanation. So we said this is a water pouring algorithm when there is channel state information available at the transmitter, and we said if this is inverse of SNR levels, this is the amount of power that is allocated in each of the links. Now if all the eigenvalues are the same, so then SNR is also the same. In that case, the power allocated would also be the same. Power allocated in all of them being the same means RSS is equal to I of m. So there again we see that if equal power is allocated under such conditions, so that means when you have very high SNR, all you need to know is the rank of the channel and you can give equal power to them, whereas when SNR is low and when eigenvalues are not equal, in that case it is better that you identify the rank of the channel and allocate power to those modes where the eigenvalues are non-zero or where eigenvalues are significant, and you give the power depending upon the strength of the eigenvalue. We will also see another important aspect in the next lecture, where we will talk about the impact of large M, or as HW channel for M being very large, what happens on outage capacity. So thank you for attending this particular lecture.